Hey team, and welcome to the virtual lecture on 11.1, the So the photoelectric effect is one of the most important observations and ultimately one of the most important explanations in the world of modern physics. Really, this experiment and then Einstein's explanation of this observation and this phenomena is what led to the theory of quantum mechanics. We're going to talk a little bit more about quantum mechanics later, but ultimately quantum mechanics is what has really allowed us to understand subatomic particles, understand how atoms and electrons work and move and interact with one another, and has set up the stage for ultimately string theory, which is currently what physicists are working on. So a lot of this might seem a little bit abstract to you, but just know that it's why we have made such great leaps and bounds is because Hertz was the one who identified this observation, and then Einstein later explained it. Here are our objectives for today. We want to describe the photoelectric effect, describe the effect on that effect of changing light intensity or wavelength. We want to describe the historical significance of the photoelectric effect, and ultimately we want to perform a bunch of calculations. So this is going to be the both C and B level videos combined. I will tell you when the B level starts so you can pause it, work on the C level questions, and then replay it when you're ready for the B level. But it made the most sense for this particular topic to combine those two lectures into one. So what is the photoelectric effect? Ultimately, what Hertz observed in the lab is that when he shone light on certain metals like zinc, those metals became positive. Ultimately, what this led scientists to believe is that when light shone on certain metals, we call them photoactive metals, then electrons actually jumped off of the surface of the metal. So instead of light reflecting off, electrons actually bounced off of the metal. So scientists really wanted to understand why this was the case. Now, up until this point in time when Hertz observed the photoelectric effect, scientists described light as an electromagnetic wave. We've even talked about light as a wave in the last unit. So we know that the energy of a wave is related to its amplitude. And scientists at the time thought that the intensity of a wave was the amplitude. So scientists predicted that if you increased the intensity or the brightness of that light, then the kinetic energy of the electrons coming off of that metal would increase. Furthermore, they thought that as long as the intensity of the light was bright enough, regardless of color, regardless of frequency, that eventually you'd get electrons popping off of that metal. What actually happened, however, was startling and mind-boggling to physicists. They realized that increasing the intensity of light didn't change the kinetic energy of those electrons at all. They still observed the same kinetic energies of the electrons being emitted from that metal, but they just observed more electrons coming off. So we realized intensity was related to number of electrons, not energy. Furthermore, they realized that electron emittance didn't depend on the intensity, but on the frequency. So you couldn't necessarily shine red light on a metal and have electrons pop off. It didn't matter how bright that red light was. If you didn't have a high enough frequency, those electrons wouldn't come off of the metal. So we say that there is a certain frequency or a threshold frequency that physicists needed to use to get electrons to come off of that metal. Finally, after taking some measurements, scientists realized that the kinetic energy of those emitted electrons was actually proportional to the frequency of the light coming on. So not only did you have to pass a certain frequency, that after you increased that frequency, then the kinetic energy of electrons increased as well. So let's check to make sure you really got what happened in this experiment correct. So let's say we have green light and it's shown on a particular metal and it causes electrons to be released with basically no kinetic energy. So if I increased the green light, what would happen to those electrons? If you said that more electrons would be released with the same amount of kinetic energy, you're absolutely right. So again, we're not changing the frequency of this light, we're just changing intensity. Therefore, we're going to release more electrons with no effect to the energy. Now what do you think would happen if instead we shone red light instead of green light? If you said that no electrons would be emitted, you're correct. So based on the problem prompt, the fact that green light releases electrons with basically no kinetic energy means that's our threshold frequency. That is the minimum frequency that we can have in order to have electrons released. Red light has a lower frequency, and therefore no electrons are going to be released from that metal. This goes back to our electromagnetic spectrum, so if you still need to memorize your electromagnetic spectrum, go back, rewatch the 10.3 video, and make sure you get that electromagnetic spectrum down. Last question, what would happen if UV light was shown instead of either red or green light? If you said that the electrons would be emitted with a greater kinetic energy, you're correct. So again, now we're increasing frequency, and increasing the frequency will increase the kinetic energy of those emitted electrons. So ultimately, after scientists realized what was going on with the photoelectric effect, they came up with a new theory. And that theory was that light wasn't just a wave. Light, even though it behaves like a wave, is actually carried in discrete packets like particles. We call this wave-particle duality. So light is basically both a wave and a particle at the same time, which is awesome. Next, scientists discovered that the amount of energy in the packet for that light depended on the frequency of that light. And it was the same for all the same frequencies. All right. Lastly, these packets represented the smallest discrete measurable amount of energy in these light waves. And scientists named these packets photons. But more important, photons are actually quanta of light. And quantum, by definition, is the smallest measurable amount of any substance. So for example, an electron is the smallest measurable amount of that negative charge energy in a lepton that we currently can measure. So ultimately, this photoelectric effect that people observed set up the stage for a new theory of quantum mechanics. Quantum mechanics relies on the fact that both light and electrons exhibit wave-particle duality. And so quantum mechanics started modeling the behavior of light and electrons as waves. But the energy in those particles was actually carried like a particle. And so this led to some really, really interesting math, some really interesting physics, and it's actually things that we're still studying today. So we just covered the first 3 objectives correlated with the photoelectric effect. I highly encourage you, if any of this was confusing, to go back and rewatch this video, or to go to your reading. The reading actually has additional pictures in it, as well as graphs that also really help visualize just this concept. I'm going to move on now to the B-level part of this lecture. So if you want to pause the video now and try to answer the C-level practice problems, I highly encourage that. And then when you're done with those, come back, play this video again, and watch the rest of the B-level lecture. So what we're going to talk about now is what Albert Einstein did to help out scientists who, even though they observed the photoelectric effect, they couldn't necessarily explain it. So Einstein was the one who in 1905 was correctly able to mathematically describe the photoelectric effect. And for this he won the Nobel Prize. And so the great thing about this is that this math is not terribly advanced. It doesn't involve calculus, it doesn't involve chaos theory, anything like that. It's really just algebra. And furthermore, Albert Einstein discovered all of this while he was working at a patent office. He wasn't working at a university, he wasn't a professor. He discovered this on his own. which is why it's so important for everyday individuals like you and like me who aren't physicists working in a research lab, to make sure that we stay current on what's going in the world of physics, and really try to make sense out of all of it, because this isn't just material for scientists in the lab, it's stuff for us as well. So let's move on to these equations. But before we do, we need a few definitions. So like I had mentioned earlier in the lecture, the photons needed to have a certain amount of energy in order to get electrons to bounce off of that metal. And the minimum amount of energy needed to bounce one of those electrons off of that metal is called the work function of that metal. It's a property of the metal. So zinc, for example, might have a different work function than sodium. And that's just, again, the amount of energy it needs to take one of the electrons in the highest energy level of sodium or zinc and kick it all the way off so that it actually escapes the electric pull of the nucleus of that atom. The photon that has the frequency corresponding to that energy is called the threshold frequency. So we oftentimes use the threshold frequency to actually calculate the work function of a metal. Lastly, we're going to deal with a concept called the stopping potential. So the way that scientists actually measured the kinetic energy of photons and electrons, well, not photons, electrons in the lab once they were emitted from the metal, was they actually put it into a circuit, and they put a voltage across the circuit, and the voltage that was actually able to stop those electrons was called the stopping voltage, and this helped us calculate the kinetic energy of those emitted electrons. So reminders from last unit, we're going to use all of these equations today and these constants. So write them down, keep them in the back of your head. No, you don't need to memorize them, but yes, you absolutely should keep this in the back of your head as we're going to use these. Next, I do want to introduce a new unit for energy. So up until now, we've been using the joule to describe energy. Once you get to the quantum scale, you're dealing with really, really small amounts of energy, and most of those amounts are on the order of 10 to the negative 19th joules. Now, scientists get lazy, and we get sick of writing something times 10 to the negative 19th joules. So scientists actually came up with a new unit called the electron volt, and 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. It's the equivalent of taking 1 electron's worth of charge and multiplying it by a volt. And it just makes all of the calculations a lot easier for scientists so that they don't have to deal with these tiny numbers. We're still going to continue to convert everything into joules and work with everything in joules, but I just want to make you aware that you will have to do that conversion. So here are Einstein's equations. So Einstein knew that the energy of a photon was proportional to its frequency. So E equals hf. The energy of a photon is equal to Planck's constant times its frequency. Now, Einstein actually discovered this by first looking at the photoelectric effect. And so he realized that the kinetic energy of a released photon was equal to Planck's constant times the frequency of that photon, but minus this constant work function of the metal, that discrete amount of energy that was required to, jack an electron from the highest energy level of that metal. And so he described that work function also in terms of the threshold frequency to keep it consistent with this Planck's constant idea, so that work function was actually Planck's constant times the threshold frequency. And lastly, we know that since the work done in moving a charge through an electric potential is equal to Q times delta V, the kinetic energy and work is also the change in kinetic energy, we know actually that the maximum kinetic energy of an electron emitted from that photoelectric surface is actually equal to the work required to stop that particular electron, which is equal to the charge of an electron, E, times that stopping potential. Okay? So let's see these in action in a practice. So let's say we have an electron with a maximum stopping potential of 4 volts. It's ejected from a metal with a work function of 2.2 electron volts. we want to determine the frequency of the incident wavelength that caused the ejection of this electron. First, I'm going to write out what do I know, what do I want to know. So I'm told that my stopping potential is 4 volts, my work function is 2.2 electron volts, and I'm looking for the frequency of my incident wavelength. Next, I want to do my conversions, so I convert my work function from electron volts into joules by multiplying by 1.6 times 10 to the negative 19th. And next, the only equation that I know dealing with the photoelectric effect and work functions that solves for frequency is my kinetic energy of that electron is equal to Planck's constant times F minus the work function of that metal. However, I realize I'm missing a variable. I'm missing my kinetic energy. So is there another way to solve for the maximum kinetic energy of that electron using the information that I have? Now, in fact, I think back and I remember, oh right, the way that scientists actually were able to figure out the maximum kinetic energy of that electron in the first place was by using a stopping potential. And so I go back, I use my equation, maximum kinetic energy equals E times my stopping potential, plug and chug, and I get that my maximum kinetic energy is in fact equal to 6.4 times 10 to the negative 19th joules. Now this is something I can plug into my other equation. From here, it's just ultimately I end up with my frequency equal to 1.19 times 10 to the 15th hertz, or 1,190 terahertz. And again, remember those Greek prefixes. If you don't have them down, go back, get them down. If any of this was confusing to you, please go back, rewatch, rework this problem. What's coming up next is a sample problem where you can check. Go ahead, take the time now to read this problem, try to solve it, pause the video, and when you're ready to see the answer, press play. Did you get that your stopping potential is 5.02 volts? If so, you're absolutely correct. You are on the right track, and you are ready to tackle the B-level practice problems on your handout. If you're still confused, please go back, rewatch this video, go back to your B-level reading, look through that example on that handout, or feel free to text, call, email, or ask questions in class on Monday. Other than that, you have gone through and hopefully mastered all of our objectives for this particular lesson. Happy practice problem solving, and I will see you in lecture 11.2.